All right, in this example, what I want to do is introduce the idea of the classical method of hypothesis testing. This will be kind of a continuation of what we did in the previous video, where we introduced the language of hypothesis testing. So if you haven't seen that already, watch that one, because I'm going to assume you know all the ideas with the language of hypothesis testing. What I'm going to do is I'm going to redo this example that's in green up here, where the claim is that taking vitamin C decreases the frequency of kids' sickness, and we test that by randomly selecting 100 kids and giving them vitamin C and finding out that in that sample they got sick 2.3 times on average per year. And we have this baseline value, this population average of all kids, not talking about vitamin C at all, of getting sick 2.5 times per year with the standard deviation of 0.9 times per year. And we want to see if we can conclude with 95% certainty that taking vitamin C decreases the frequency of kids' sickness. So what I did, so I don't have to keep referring back to that, is I copied that down here. So repeating this example, the claim is that vitamin C decreases sickness, and the relevant information is mu naught, the population average, this baseline value is 2.5, sigma, the standard deviation, the spread of the parent distribution is 0.9, that's also a population parameter, x bar, the sample average, the 100 kids who took vitamin C all the time, on average they got sick 2.3 times, and our level of certainty corresponds with an alpha value of 5%. Because 100% minus 95% gives us this 5%. So our claim that vitamin C decreases sickness, if I asked you this on a test, it would be 4 steps. Your first step is you would state your null and alternative hypotheses. And as we saw in the previous video, your null and alternative hypotheses in this section are always going to compare mu and mu naught. Mu will always be the symbol mu. Mu naught will always be a number given to in the problem, 2.5. And for your null hypothesis, it will always be that mu equals mu naught. For your alternative hypothesis, it'll be based upon the claim that's being made. So this word decreases is what tells me to put a less than sign here. Because I put a less than sign here, this is what's called a left-tailed test, and it's optional if you want to make note that this is a left-tailed test. You don't have to, but I typically do. And as we saw in the last video, you're going to be drawing a picture in step 3. And when you draw a picture in this class, I want you to give context to your picture. So we got a shape, center, and spread. And this is the shape, center, and spread of the sampling distribution. So the shape will end up being approximately normal. And that's because of the central limit theorem. We don't know the shape of the parent distribution, but it turns out it doesn't matter. The central limit theorem tells us that as long as our sample size is large enough, the sampling distribution is approximately normal. N greater than or equal to 30 is the criteria that we use, our cutoff. N is 100, greater than or equal to 30, we get normality of our sampling distribution. The center, the short answer is that the center is given by mu naught. The long answer is the center is given by mu, but we assume the null hypothesis is correct, so mu is equal to mu naught. And the spread, since this is the sampling distribution and not the parent distribution, is not just sigma, but sigma divided by the square root of n, so 0.9 divided by the square root of 100. Went through all that really quickly because we did it in the previous video. Where I want to spend some time is in step 3 here. And step 3 is where you draw the picture. And there's 2 different pictures that you can draw. And in this picture, in this video, we're going to draw the picture for the classical method. In the next video, over to the side, we'll draw the picture for the p-value method of hypothesis testing. But in this video, just the classical method. So when you're drawing your picture for the classical method, there's 3 things that I want you to include. I want you to include alpha. I want you to show me your critical value. And maybe I'll write value and then in parentheses I'll put an S because sometimes there's more than one. And then I want you to show me your test statistic. So early on especially, I'll prompt you to make sure you tell me all 3 of these. But going forward, it'll just be known that when you're doing the classical method of hypothesis testing, your picture should include these 3 things. So how do you do it? How do you draw your picture? Well, above we said that the shape is approximately normal. So let's start out with a distribution that's normal, or approximately normal. Draw it as best you can. That gets you here. You might think that the next step would be to include the center here, this 2.5. And you kind of do and you kind of don't. You want to signify your center, but you're not going to signify it with the number 2.5 because in this picture we're going to use what are called normalized values. And all that means is we're going to quote z-scores. So I'm going to put a 0 in the middle, but really that 0 means, it's a weird looking 0, that 0 means 2.5. That means 0 of these spreads above or below this 2.5. All of these will be normalized values, think z-scores, because we're going to end up using our calculator to get our test statistic, and your calculator gives you this as a normalized value. So in order for it to make sense with the rest of the numbers you put here, these all have to be normalized values. The short answer, you always put a 0 in the center, even though you wrote that the center is 2.5 up here, because the reader knows enough to recognize, oh, these are just normalized values, and you're telling me the real center is 2.5. The z-score of that center would just be a 0. Next thing you want to include is alpha. Alpha is always the total area of what's called the rejection region. Some books call it the critical region. I think rejection region is more informative, so that's what I'm going to call it. Alpha is always the total area of your rejection region. So in this case, alpha is 5%. I have to draw a region that has a total area of 5%. Where do I put that region? Well, it depends. In this test, it's a left-tailed test, so I'm going to put 5% over on the left here. So here I am shading in alpha. This is 5%. I've just shown the reader alpha. Note it's on the left because it's a left-tailed test. If this were a greater than sign, it would be a right-tailed test, and I'd put 5% over on the right. And we'll do that in another example in this video. And if it were a two-tailed test, if I put a does not equal sign here, then the total area is supposed to be 5%, but it has to show up on the left and the right, so I better put 2.5% on the left and 2.5% on the right. But we'll get to all that later. Alpha is now depicted in this picture, and it's on the left side of my distribution because it's a left-tailed test. In a minute, my calculator will tell me my test statistic. And the way I'll make my conclusion, it'll be a yes or no thing. Is that test statistic in this rejection region? Is it in the shaded region or not? That's all you got to figure out. So your calculator is going to give you a number, and you just got to figure out, is that number in this shaded region? Well, think about it. How are you going to do that right now? Right? You don't know where this shaded region starts. If you don't know where the shaded region starts, when say your calculator tells you this test statistic's -2.5. Is that in this shaded region? I don't know, because I don't know where the region starts. You need to first figure out where the region starts so that you can tell if your test statistic is in that rejection region. The spot where your rejection region starts is what's called the critical value. Note that you could have critical values because you could have some rejection region over here and over here if it were a two-tailed test. But in this case, it's a one-tailed test. My rejection region's all the way over on the left, so I only have one critical value, and it's right there. Critical value is just the point at which your rejection region starts, and we need to find that. We need to find that, and it needs to be a normalized value, a z-score, because all of the numbers when we deal with hypothesis testing are normalized. So I need you to find the z-score that is so far to the left that the area left of it is only 5%. And I think you know how to do that. I think that's something we've already done in this class. Use the inverse norm function on your calculator. When you use inverse norm, it's always going to want 3 inputs. It's always going to want the area to the left of the point you're talking about. In this case, that area is 5%. Note that if that 5% were on the right, the area left of it would be 95%. More on that in the next example. And then the center and the spread. It's tempting to put in 2.5 and this expression for your center and your spread. But if you do that, what you'll get are numbers of sicknesses down here, not z-scores. In order to make sure that you get normalized values, z-scores down on the bottom of your distribution, you got to put in a 0 and a 1 here and here. We saw that when we were calculating z sub alpha over 2 in the confidence interval section, that the center and the spread were always 0 and 1. Same when you're dealing with hypothesis testing, trying to find your critical value. Type this into your calculator. I think what you'll end up getting is -1.645. You do enough of these, you start to memorize these values. In case you don't believe me, I'll hit second and then variables to get into the distribution menu. Go down to inverse norm. Tell my calculator the area to the left of the point I want is 0.05. The center is 0 and the spread is 1, so that I get normalized values. And it spits out this -1.645 if you round it to 3 decimal places. That's where this number came from. Now all I got to do is get my test statistic, and what my conclusion will be is my test statistic in the rejection region? That's all it is. So let's get my test statistic. The way you get your test statistics also out of your calculator. But it's in a different menu. It's under the stat menu in your calculator. If you go over to the tests column, where we were for the z interval function in the previous section, you'll see something called z-test. all of these first 6 things here, all correspond with hypothesis testing. But in this section, we're doing Z testing. We don't really understand why we're doing Z testing now because we haven't seen any other types of testing. But when we learn other types of testing, I'll be able to explain why we're doing Z testing now. The short answer is because you have sigma. Sigma, the population standard deviation, was given to you, so it's a Z test. At any rate, select Z test. Z test, just like Z interval, can be done whether you have data or statistics. Whether you have the first kid got sick 3 times, the second kid got sick 2 times, you can put all that in a list. Typically in this class, you'll have statistics about the data instead. You'll have mu naught and sigma and X bar and N. And it asks for exactly the things that we wrote down up here. Mu naught was 2.5. Sigma, not the spread, but sigma. I know it wants sigma because it wants sigma and N. It will calculate the spread based on those 2 values. So sigma is 0.9. X bar was 2.3. And N was 100. And now I've input all the numbers that this calculator function needs. But there's one more row it needs. This guy right here. What's this row asking for? It's asking what's your alternative hypothesis, what's your claim. So remember, it can either be mu does not equal mu naught, mu is less than mu naught, or mu is greater than mu naught. Mu naught is this 2.5. Right, so I'm telling my calculator, my claim is that mu is less than mu naught. Of these 3, this is the one that says mu is less than mu naught. And if you do all that, you can then go down to either calculate or draw. I'm going to tell you that whenever I use the classical method, I use the calculate function here. You'll be able to do either one. Maybe I'll show you draw in the next video. For this one, just hit calculate. And this is what we'll get output from your calculator. It gives you a lot of information. The only one that's relevant for the classical method of hypothesis testing is your test statistic, which is signified with a Z here. It's a Z because it's a Z-score down here. It's negative 2.22. So my question to you is that negative 2.22, is that in the rejection region or not? Well, 0's here, negative 1.645's here. So yeah, because negative 2.2 is further to the left of the negative 1.645, it would be in the rejection region. So put it anywhere out here. It doesn't matter where, just make it clear that it's in the rejection region. Typically people signify it with a Z. Z equals negative 2.22. I don't care too much about the rounding. We won't have a case where the test statistic is all that close to the critical value. So it doesn't really matter how you round. You'll be able to tell that this is in the rejection region. Here's your picture for the classical method of hypothesis testing. That's it. Step 4, draw your conclusion. Your conclusion is going to include 3 things, just like your picture up here included 3 things. Those 3 things will be kind of why you're doing what you're doing, what that means for the null hypothesis, what that means in the language of statistics, and kind of what that means in context. And what you'll see is the first time I write this down, you'll be a little bit overwhelmed. You'll be like, wow, I'm never going to remember all that. And then you'll be like, oh, it's the exact same each time. We're going to do this like 20 times in this class, and you'll get the hang of writing these conclusions. So why you're doing what you're doing, it comes down to yes or no, is your test statistic in the rejection region? In this case, it is. So I would say because test statistic, or my test statistic if you want, and I like to restate it here, you don't have to. In this case, it was negative 2.22. Because the test statistic falls in the rejection region, so that's kind of the why I'm doing what I'm doing. And then what that means for the null hypothesis. Well, if the test statistic falls in the rejection region, essentially what that means is you just got a really strange result, right? My sample average, I expect that to be close to my population average, but it's not. It's really far out here in the tail. It's in the rejection region. That's a really strange result. If this center really is true, it's really strange for me to get a result this extreme. What's going on here is we're assuming the null hypothesis is true when we put this as the center. When we put 2.5 as the center, we're assuming that mu equals 2.5. And we're saying if the population average number of times that people get sick while taking vitamin C is 2.5, is pretty unlikely that my sample average would be as low as 2.3 because this is in the rejection region. Because my test statistic falls in the rejection region, The phrase that's typically used is there is sufficient evidence. I'm not going to be super picky on that. The part that I want to make sure you get is there's sufficient evidence to reject the null hypothesis. Test statistic is in the rejection region, means a strange result. Strange result means you reject the null hypothesis. Why you're doing what you're doing, what it means in terms of the null hypothesis. But yeah, what's that mean? What do you mean reject the null hypothesis? Well, as we saw in the previous video, when you get a strange result, you reject the null hypothesis, that means that your claim is true. So my claim was that vitamin C decreases sicknesses. So what I would say is, so I can conclude that vitamin C decreases sicknesses for these kids. Sure, leave it like that. So note the three things here. Because my test statistic falls in the rejection region, there is sufficient evidence to reject the null hypothesis. So I can conclude that vitamin C decreases sickness. Seems like a lot. It doesn't have to be this verbatim. But what you'll see is when you do a few of these, it helps to write them so that they look like this. A couple minor things I want to talk about before I end this video. What if this problem were different? All right, what if I changed it so that my alternative hypothesis, so maybe this is example 2, same, except the claim is that vitamin C increases sicknesses. And maybe so that it makes sense to be claiming that vitamin C increases sicknesses, we'll suppose that X bar was 2.6. Right? My baseline level of sicknesses, remember, was 2.5. So if my claim is that it increases sicknesses, it would kind of make sense that my sample average was greater than the 2.5 instead of less than the 2.5. So suppose you're redoing the whole thing, but now your claim is that vitamin C increases sicknesses and that X bar is 2.6. Everything else is the same. Let's go through this really quickly. Null hypothesis is the same. Mu equals mu naught, that's 2.5. Alternative hypothesis is different now. You're still comparing mu and mu naught, but now that your claim is increases sicknesses, you put a greater than sign here. This is now a right-tailed test, not a left-tailed test. Shape, center, spread, same. Maybe for shorthand purposes, I won't even bother rewriting it. It's the exact same as it was before. The shape is still approximately normal because n is still greater than or equal to 30. The center is still mu naught, which is still 2.5, and the spread is still sigma divided by the square root of n. It's all the exact same. What changes is my picture. When I'm drawing my picture, again, for the classical method of hypothesis testing, because it's a right-tailed test, I want my rejection region to be over here on the right. So this area is 5%. I still need to know my critical value. I'm still putting 0 in the middle. I still want normalized values. But now to figure out this critical value, I'm going to use inverse norm. And the area to the left of the point I'm looking for is 95%. I still want a z-score, so it's still 0 and 1. You put that into your calculator, you'll end up getting positive 1.645. Oh yeah, that makes sense. Right? I'm kind of the same distance left and right of this 0. So because of symmetry, it's got to be positive 1.645. Don't believe me? Type this into your calculator. And then you'll go and you'll hit the stat key. And you'll go over to tests and go down to z-test because you need your test statistic. Got to figure out, is the test statistic going to be in this rejection region? Well, I have statistics. Mu naught still 2.5. Sigma still 2.9. Now X bar is 2.6. Remember, we're assuming that we're changing X bar. And now my claim is that mu is greater than mu naught. So I select this third one. When I go down to calculate it, it'll give me a new test statistic. Now my test statistic is 1.11111. That's not in my rejection region, right? That's somewhere in between 0 and the 1.645. Maybe that's, I don't know, right here. Sure. Maybe I should have spaced these out so it was easier to write it. There's my test statistic. This would be my new picture under these new assumptions. Conclusion? Be almost identical to what you wrote here. I'm going to write the same thing, and then I'll go back and show you that I'm only going to add the word not 3 times. what I would say is because the test statistic, which in this case was 1.11, again, you don't need to write what it is, I just like to do that, does not fall in the rejection region. And you don't need to underline the word not, I'm just trying to highlight the differences. That's why we're doing what we're doing. What's that mean for the null hypothesis? There is not sufficient evidence to reject the null hypothesis. Maybe I'll drop it down a line just so you can really see the three different parts. So I cannot conclude that vitamin C, whatever my claim was, in this case, vitamin C increases sicknesses. Right, remember for this new example, we changed the claim to be that vitamin C increases sicknesses. One more, I know this video is getting long, but this last one will be even shorter than the one I did before that. I'm gonna call it example 3. X bar is still 2.6. Claim, everything else is the same. Claim is that vitamin C affects, it's a verb, I think affects number of sicknesses. All right, so I would have given you the whole scenario, and then the last sentence would have said that it affects the number of sicknesses, as opposed to it increases the number of sicknesses like we saw in example 2, or it decreases the number of sicknesses like we saw in example 1. Well, if you see the word affects, if it doesn't specify whether it makes them bigger or smaller, you have what's called a two-tailed test. Your null hypothesis is still that mu equals mu naught. Your alternative hypothesis is that mu does not equal mu naught. I don't know if it's greater than or less than, it just says affects here. This is what's called a two-tailed test. Don't have to write that it's a two-tailed test, I just like to. Shape, center, spread is all the exact same. I'm not even going to bother writing that. Here's step 1, 2, it's all the exact same. 3, I'm going to draw my picture. Still want to include those same 3 things. Still want it to be approximately normal, best you can draw. Still want to put 0 in the middle. That 0 represents the 2.5. I still want the area of my rejection region to be 5%. But now that it's two-tailed, I need some of it over here and some of it over here. How much? Well, if 5% is shaded in total, 2.5% is on each side. So now I could use inverse norm twice to find out my 2 critical values. To find out this critical value, the area to the left of the point that I'm looking for is 2.5%. I'll put in 0 and 1 so that I get normalized values. End up getting negative 1.96. In case you don't believe me, let me show you. Inverse norm, the area to the left is 0.025, and the center and the spread are 0 and 1 respectively. That gives me this negative 1.96. And you could do that exact same thing to find out this number. Inverse norm 0.975, I guess would be the area to the left here. Although if you're really clever, you might recognize that because of symmetry, if this is negative 1.96, this has to be positive 1.96. And then I go to my calculator to get my test statistics. Stat, tests, z-test. I tell my calculator I have statistics. Mu naught is still 2.5, 0.9. All this is the exact same. The first thing that changes is this line. This is my claim. Now my alternative hypothesis is that mu does not equal mu naught. So I'll select the first thing and hit calculate. What you'll see is it leaves the test statistic alone. Z equals 1.11 again in this example. So that's going to show up somewhere in here. And similarly to example 2, my test statistic is not in the rejection region. So maybe for step 4, I'll say same, and that gets quotation marks because it's almost the same as example 2. And why I'm putting quotation marks is you'll say because the test statistic does not fall in the rejection region, that's the exact same. There is not sufficient evidence to reject the null hypothesis. That's the same. So I cannot conclude that vitamin C, you wouldn't say increases, you'd say affects. Maybe I'll write that. Dot, 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 cannot conclude that vitamin C affects, because that's what your claim was, sicknesses. Those are the three different types of hypothesis tests that you can see with the classical method. They're left-tailed, right-tailed, or two-tailed. And if you can follow those three examples, that's really good. This stuff is pretty challenging. I'm going to go back and show you a different way you can do these, which is called the p-value method. And then if you have your head wrapped around all of that, you understand probably the most intense topic of this class, hypothesis testing.